Welcome to Forecasting Snow Squalls and Communicating Potential Transportation Impacts. I'm Pete Banakis, Lead Meteorologist with the National Weather Service in Burlington, Vermont. In this presentation, we'll provide information on forecasting non-lake effect snow squalls as might occur in conjunction with or out ahead of Arctic cold fronts. The presentation includes results from a composite study, 2 case examples, and operational suggestions on how to communicate the transportation threat to state and local officials as well as to motorists. So let's begin. Here is an outline of what will be covered in this presentation. We'll begin by providing background information on snow squalls and their societal impacts. We'll then jump to synoptic and mesoscale environments conducive for snow squalls based on a composite study of 36 events, and discuss some of the dynamics relevant to these systems. Next, we'll talk about the snow squall parameter, which was developed as a situational awareness aid for forecasters, and describe the research development and subsequent move into operations. Even the best forecast is useless if not properly conveyed, so we'll discuss means of effectively communicating the threat associated with snow squalls. It should be noted that this presentation is based on a journal article written by National Weather Service forecasters Andrew Lecanto, Greg DeVore, and myself, which is available in the National Weather Association Journal of Operational Meteorology. We can't cover everything in this talk, but further details can be found in the paper at the URL listed on the slide and in the description box below. So we might begin by asking, what is a snow squall? In a sentence, it's a mesoscale convective system producing gusty winds and heavy snow. It's useful to think of snow squalls in this way as they develop in moist, unstable regimes with surface-based cape present and generally become organized owing to strong frontal and upscale synoptic forcing. Hopefully I can convince you that this is the case by the end of the presentation. These events tend to be short-lived, marked by a burst of heavy snow, a sharp increase in wind and wind gusts, and a temperature drop. They tend not to reach National Weather Service snow advisory criteria, which is 4 inches across Vermont and northern New York. The falling temperatures can produce a flash freeze situation in which snow that initially melts on pavement contact then refreezes into a thin layer of ice as temperatures drop. The associated icy road conditions can persist on untreated surfaces for hours following a snow squall. These systems can have deadly consequences for travelers. They also fit a category of events called High Impact Subadvisory or HISA events, in which the traditional National Weather Service product suite doesn't necessarily convey the proper message. In the radar and webcam loop here, you might envision a casual recipient of forecast information who may have heard something like a 30% chance of snow showers this evening before departing for their destination. Such a driver may experience anxiety and apprehension as they suddenly encounter whiteout conditions. As such, snow squalls can result in a greater number of accidents, in a manner similar to the first snowfall of the season when drivers are unaccustomed to winter conditions. The displayed radar and webcam animation here from 30 November 2007 shows base reflectivity from the Fort Drum, New York radar time matched with a webcam from Potsdam, New York. The sudden drop in visibility and heavy snow and typical increase in wind and drop in temperature are a signature aspect of snow squalls. A snow squall possesses characteristic features similar to a warm season squall line. This Meteogram from Messina, New York on 2 March 2011 documents passage of a snow squall around 14Z. Associated heavy snow results in a sudden drop in visibility down to 1/4 statute mile. There is a coincident drop in surface temperatures, an increase in dew point and relative humidity. Temperatures continue to fall throughout the day following the squall and cold frontal passage. Snow that initially melts on the roadways has the potential to later freeze in sub-freezing temperatures thereafter, which can be a lingering consequence of snow squalls for many hours. The Meteogram also shows a peak in wind speed and wind gust along with a wind shift with the snow squall. Surface pressures rise as well following the squall passage. Unfortunately, there is a long history of deadly accidents with snow squalls. A common aspect of these events is that snow accumulations are quite small, typically an inch or less. Pictured here are some snow squall events from winter 2012-2013. Our overall goal is to anticipate these types of events and hopefully mitigate the adverse societal impacts which are caused primarily by dangerous driving conditions. Most of what has been done previously on non-lake effect snow squalls has been limited to a few select case studies. One exception was the Windex forecast technique developed by Lundstedt in the early 1990s. This technique is reliant upon the textural FOOS output available for select cities from the NCEP models, and was originally developed against the NGM. Our goal was to create a composite study or climatology from which we could develop some useful forecast information for these types of systems and a more graphical or visual approach for forecaster assessment. As we'll see, cold season or low dew point mesoscale convective systems, as documented by Corfiti et al. In 2006, also show environmental similarities to snow squalls despite obvious differences in precipitation type. In addition to learning more about the snow squall environment and associated system dynamics, we ultimately use this information to set up forecast visualization tools and a snow squall parameter to aid in forecaster situational awareness. Also, operational messaging, education, and public partnerships are necessary to effectively communicate the transportation threat posed by snow squalls. The end result of this study is hoped to be more certainty in forecast products, better communication, and action taken on the part of road crews in terms of strategic placement of resources and even pre-treatment of roadways. In terms of the research that was performed, 3 ASOS sites in the WFO Burlington, Vermont forecast area were used to create the database of snow squall cases. These were Messina, New York, Burlington, Vermont, and Montpelier, Vermont. Moderate and heavy snow observations were searched over a 10-year period and filtered based on surface wind direction. The filtering was needed to limit the data to a more manageable size by removing the majority of moderate to heavy snow observations associated with nor'easters. Each moderate to heavy snow observation with a westerly wind component was then further verified using 2-kilometer composite reflectivity data. A total of 36 snow squall cases were found during the period, and surface data characteristics were logged for each event for further analysis. Here are 2 snow squall radar examples. The radar reflectivity depiction of snow squalls resemble that of a traditional squall line, except echotops and the depth of the convection tends to be much lower, typically between 2 and 4 kilometers AGL. A few of the events in our database involved pre-existing lake effect snow streamers off Lake Ontario, such as the example on the right, where the snow band becomes entrained in the airflow in advance of a secondary frontal boundary or shortwave trough moving in from the west. This tended to add to the intensity and duration of the individual events. The 6 hybrid events were otherwise treated identically to the standard cases, with a composite analysis performed based on the grand total of 36 events. We'll now examine surface and synoptic features based on our snow squall database. We'll begin with a look at how long the low visibilities lasted at our 3 sites. Consistent with our own experiences, snow squalls are short-lived events. Here is a box and whisker chart showing the duration in minutes of the moderate and or heavy snow associated with the snow squalls based on the ASOS observations. It was found that the middle 50% of cases, falling between the 25th and 75th percentiles, experienced a 14 to 24 minute period of heavy snow and a 15 to 36 minute period of moderate snow. However, durations of heavy snow were as few as 4 minutes and as much as 47 minutes, while for moderate snow, durations range from 3 minutes to almost an hour and a half. The median length of heavy snow lasted 17 minutes, and the median length of moderate snow lasted 26 minutes, which is denoted by the horizontal line within the box plot. You can also see at the top of the graphic that heavy snow occurred in 30 out of the 36 snow squall events. We can further examine temporal aspects of these events by looking at their hourly and monthly distribution. In the diurnal graphic in the upper left, we found that snow squalls were more common during the daylight hours. Only 11 cases occurred between 0 and 12Z, with 25 cases occurring between 13Z and 23Z. Although the sun angle is low during the winter months, surface-based instability is still more likely to occur during the daytime than it is at night, which likely contributes to the observed diurnal distribution since snow squalls are convective features. Snow squalls were observed in all months between November and March, as shown in the lower right graphic, with a slight peak with 10 events in February. Burlington, Vermont, airport code BTV, has a contract weather observer to augment ASOS. So, for the 21 cases affecting Burlington, we were able to extract some additional information based on the snowfall measurements taken by the observer. As expected, snowfall associated with the squalls generally amounted to only around 1 inch, based on the hourly change in how much snow was on the snowboard. The snowfall over a 12-hour period had a median value of just 1.6 inches, which is well below the snow advisory criteria. Likewise, the liquid equivalent amounts are quite small, with most events just several hundredths of an inch. The snow to liquid ratios on the right tend to be relatively large with these events, around 20 to 1, which is a function of the continental origins and westerly to northwesterly flow associated with the weather systems that tend to produce the snow squalls. For example, Arctic cold fronts. We'll look now at some composite results from the North American Regional Reanalysis, or NAR, for the 36 cases using tools from the SROL website, listed on the page. At 300 millibars, the composite mean pattern includes a broad trough across New York, New England, and across adjacent sections of southeastern Canada. There was a large negative height anomaly, averaging 200 meters across the area associated with the trough. The mean heights and winds indicate a strong upper jet across the upper Ohio Valley eastward, across the mid-Atlantic states, and points offshore. There is split upper flow across the CONUS with indication of polar and subtropical branches of the upper jet, and confluent flow along the eastern seaboard. It turns out that the Burlington forecast area was on the cyclonic shear side of the upper jet in all 36 cases. In other words, snow squalls were not observed south of the mid to upper level jet axis in our study. Here's a look at the 500 millibar composite mean height field overlaid with mean winds in meters per second, again for a composite based on our 36 snow squall cases. There is a short loop here from 3 hours before the squall time, at the NAR time closest to the squall time, and 3 hours subsequent to that. So we're covering a 6-hour period in this loop. The 500 millibar key features include cyclonic flow over the northeastern U.S. and southeastern Canada. We are once again on the cyclonic shear side of the 500 millibar jet, which was true for all 36 cases. We are also near or just upstream of the mean trough axis. For 850 millibars, we have a height and temperature composite mean in the upper left, and the height and wind composite mean in the bottom right graphic. In the 850 millibar temperature composite mean, an upstream cold front is evident with packing of the isotherms and approaching 850 millibar cold advection from Quebec and southeastern Ontario in the 6-hour loop. The strongest winds at 850 millibars are also generally south of the forecast area across Pennsylvania and the southern tier of New York, with maximum values of 16 to 20 meters per second or 35 to 40 knots. Next, we want to say a few words about BuffKit, which is a Windows-based software program used by forecasters to view and analyze model forecast soundings, as well as model time height cross-sections. A time height cross-section using NAM data is shown in the subsequent slides to shed light on the structure and environmental conditions associated with a snow squall event on 7 December 2008. While only one case is shown in this part of the talk, this case was representative of a suite of events depicting a snow squall passage across northern Vermont. Since BuffKit is an often used tool by operational National Weather Service forecasters, it's worth taking a few minutes to understand how these systems look from the perspective of a time height cross-section. So here we have a representative snow squall event from 7 December 2008 as depicted by the 12Z NAM that day. The snow squall occurred during the late afternoon hours. In the first BuffKit image, we have an overlay of relative humidity with respect to ice, which is shaded, omega, where negative equals rising motion, shown by the red contours, forecast winds, and precipitation shown by the hourly weather graph at the bottom. We do have a boundary passage around 22Z, which we will sketch onto the image here. Now note that around 20 to 22Z, there's an intense zone of omega around 20 microbars per second, which is centered around 1 kilometer AGL, accompanied by a short period of precipitation, which is a quick burst of snow. The strongest upward vertical velocity is centered in the lowest 1 to 2 kilometers AGL, which is common with these snow squalls. The dendritic snow growth, which occurs in ambient temperatures in the environment between -12 and -18 Celsius, intersect the strong upward vertical velocity, which optimizes snow growth and precipitation efficiency. The equivalent potential temperature, or theta E lines, are nearly vertical, as we see here, indicative of moist adiabatic lapse rates behind the front. In advance of the boundary, there is a zone where theta E actually decreases with height, which is by definition an area of potential instability. The isentropes, or potential temperature lines, shown here, are similarly vertically oriented behind the front, which promotes downward momentum transport behind the cold front in a well-mixed environment in vicinity of a 38 knot speed max, which can be seen here just below 1 kilometer AGL behind the front. So we have good downward mixing potential in this type of environment. When you overlay the omega field on the potential temperature field, you'll note that the strongest omega just precedes the frontal boundary. There is strong force descent associated with the frontal boundary and likely ongoing low-level frontogenetic forcing, though we can't specifically diagnose that within BuffKit. We'll demonstrate the role played by low-level frontogenesis next, and in our case studies a bit later in the presentation. So here we have a schematic showing a conceptual model of a warm season squall line developed by Bob Howes et al. 1989. I just want to briefly compare and contrast the warm season squall line with a cool season snow squall event. The line is moving from left to right in the figure, as denoted by the storm motion vector here. Toward the right-hand portion of the image, beneath the area of heaviest precipitation, the blue H represents a mesoscale high. A meso high develops as a hydrostatic consequence of rain-cooled air behind the gust front in an area of convective downdrafts and heavy precipitation. A mesoscale cold pool develops in this region through evaporative cooling effects. There is a relative low pressure in advance of the squall line, setting up a pressure couplet and strong pressure gradient across the leading edge of the warm season squall line. We also see well-developed pressure couplets in many snow squall environments, which is a strong indication of an ongoing mesoscale circulation and system organization. However, in the snow squall environment, the processes are different and less driven by the convection itself. In the snow squall environment, the updrafts and downdrafts are less intense owing to low CAPE and low moisture availability, with precipitable water values generally at or below a quarter inch. There is no water loading or evaporative cooling owing to the presence of frozen condensate, though sublimation is possible. Also, the overall system is shallower in the wintertime, generally between 2 and 4 kilometers, as opposed to 10 to 15 kilometers deep in the warm season. The upshot is that a strong surface pressure gradient develops almost entirely through baroclinic and frontoscale processes in snow squalls. Frontogenetic circulations develop along cold or Arctic fronts, which are either maintaining their intensity or intensifying further. These frontogenetic circulations can develop in an environment with a small amount of CAPE, typically less than 100 joules per kilogram, as we'll document later. The instability helps shrink the scale of the frontogenetic circulation, resulting in a very narrow line of convective updraft. The frontogenetic circulation also helps mix down stronger winds on the cold side of the circulation just behind the cold front, as we saw in the BuffKit section. This is what gives the snow squalls the gusty winds. There is typically a moist absolute unstable layer, or MAL, within the frontogenetic circulation. This means the atmosphere is saturated and has lapse rates exceeding moist adiabatic, which occurs through strong and sustained mesoscale ascent and associated cooling. So the combination of an ongoing mesoscale circulation in a cold, moist, and unstable environment brings about the basic ingredients necessary for organized lines of snow squalls along fronts. When looking at surface analyses, a strong, well-defined pressure rise-fall couplet in the surface isobaric field is an important clue that such frontogenetic circulations are occurring, and can clue the forecaster in to diagnose the situation further. Once the synoptic composites were complete, we used the GEMPACK software package to further examine a variety of variables available from the NCAR. Here is a list of some of the variables examined using GEMPAC. These variables were examined for all 36 snow squall cases, including the NAR time closest to the squall occurrence and the 3 hourly time steps immediately prior and after. Also, a control sample was generated which included every 3 hourly time step for the entire 2005-2006 winter season from November through March, which included a total of 1,208 time steps. Once the snow squall cases for that year were removed, the goal was to analyze the parameter space associated with each variable and identify differences between the control sample and the 36-case snow squall sample to better understand how the snow squall environment differed from the control. This process served two ends. First, a better physical and conceptual understanding of the snow squall environment, which could be documented for forecasters. Secondly, development of the snow squall parameter based on differences in some of the variable distributions. To show some examples, here we see a comparison between the distribution of the data in the snow squall environment versus the 2005-2006 control sample. The box and whisker graphs represent a percentile rank analysis, which allows us to visualize the distribution of the data and not just a mean or median value. For example, on the left, the 0 to 2 kilometer mean wind speed was observed to be stronger in the snow squall environment than in the control sample. Likewise, there was a small amount of CAPE in the snow squall dataset, and generally no CAPE in the control dataset. Because CAPE can only be 0 or greater, it is difficult to use this to see how close an environment might be to being unstable. For this reason, we also looked at the theta E difference between the surface and 2 kilometers AGL. For that graph on the right, you can see a large separation between the two datasets, with large positive values in the control and values clustered near to slightly below 0 for the snow squall cases. Remember, equivalent potential temperature decreasing with height means potential instability exists in that layer. In this diagram, we have a scatter plot with the 0 to 2 kilometer AGL mean RH along the abscissa and the 0 to 2 kilometer AGL equivalent potential temperature difference along the ordinate. The yellow dots represent the 36 snow squall cases, and the gray dots are from the 2005-2006 control sample. The moisture and instability parameter space in the lowest 2 kilometers AGL revealed clustering of the snow squall cases towards unstable, high relative humidity environments relative to the control sample. The clustering of data in the scatter plot highlights the potential forecast value that can be extracted from the low-level moisture and instability fields. The favored parameter space for snow squalls is in a relatively narrow zone with moist and unstable low-level conditions. So the idea was to develop a snow squall parameter to highlight favored areas for snow squalls in time and space. We've already demonstrated that snow squalls are shallow, moist, convective structures in thermal environments cold enough for the precipitation type to be snow. Thus, the necessary conditions are those for convective precipitation: moisture lift and instability, plus some background flow, and a vertical temperature structure conducive for snow. The snow squall parameter, which is a non-dimensional number, would be plotted for values greater than 0, and where the surface wet bulb temperatures were at or below 1 degree Celsius, ensuring an environment cold enough for snow. To explain this a little further, since lapse rates are steep in these convective environments, the context here is such that we only need to ensure a cold enough surface condition to ensure snow is the precipitation type. Snow squalls do not form in warm advection or overrunning environments with potential warm layers aloft. So that simplified some of the conditions quite a bit. Using a percentile rank analysis, 3 factors were normalized based on results and variables showing good separation in the snow squall sample of 36 cases versus the control sample. These included surface to 2 kilometer AGL mean RH, the surface to 2 kilometer AGL equivalent potential temperature difference, and the mean 0 to 2 kilometer AGL wind speed. This is the same type of normalization that was used to develop the significant tornado parameter and supercell composite parameter, which are popular on the Storm Prediction Center mesoanalysis page. So a similar methodology was followed to develop the snow squall parameter. Note that the snow squall parameter approaches 0 as any one of these factors approaches 0, as they are each considered to be necessary conditions. Lift or forcing must still be assessed independently, and we'll show a simple way of doing that using pressure rise-fall couplets. Lastly, it should be noted that calibration of the snow squall parameter was done using the NCAR. A limitation of this methodology is that the NCAR has a relatively coarse horizontal resolution of only 32 kilometers. Thus, when employed in a forecast setting, modern operational models tend to give higher values of the snow squall parameter, especially those running at very high resolution, say 4 kilometers or less. We'll have a better feel for the differences when we examine our two case studies a little bit later in the talk. So the snow squall parameter is one number that highlights where the environment is moist, unstable, windy, and cold enough for snow. We took our normalized equation shown in the previous slide and ran it back against our two data sets, the snow squall sample and the control sample. As can be seen in the box and whisker plot, the snow squall parameter shows excellent separation between the snow squall sample and the control sample. This is exactly what we want to see. The median value is 0 on a typical winter day, represented by the control sample, and has a median value of 1 in the snow squall sample. Again, this normalization is valid only for the NCAR, the net effect being that we'll see generally higher snow squall parameter values when using higher resolution models in an operational forecast environment. In the bottom graphic, we see the snow squall parameter plotted versus time through the entire 2005-2006 winter season. Over the 5-month period shown, the 3-hourly NCAR snow squall parameter time series shows brief intervals of positive snow squall parameter values, interspersed with much longer periods where the snow squall parameter is equal to 0. This implies a good signal-to-noise ratio that will get short time windows of favored environments for squalls, interspersed with much longer and greater periods that do not have a threat for snow squalls. Probability of detection and false alarm rate statistics for the snow squall parameter were also computed and are available in the journal article at the link in the description box below. Before we dive into the two case studies, I want to add a quick word about convective mode, or the observed geometry of what we see visually or on a radar display. Much like warm season convection, what the snow squall parameter means in terms of convective mode and organization depends on the associated low-level forcing for ascent. When there is a well-defined pressure rise-fall couplet and a low-level frontogenesis maximum co-located with positive snow squall parameter values, the snow squalls will be organized into narrow bands of strong reflectivity. The organization of the convection will generally be linear, an example of which is shown in the photo and mosaic composite reflectivity image on the left. On the other hand, if there isn't a pressure rise-fall couplet, or a boundary with a frontogenesis maximum, the presence of positive snow squall parameter values mainly signals potential for cellular snow shower activity. This activity will be less organized and generally less intense than the linearly organized events, though brief, heavy snow is possible in stronger cells. We see an example of this type of cellular event on the right. So it is important to diagnose the atmosphere beyond just the value of the snow squall parameter, or any other parameter for that matter. The nature of the large-scale and mesoscale forcing will influence the convective mode just as it does during warm season deep convective events. We now look at the application of the various diagnostics we have discussed using two case studies from 17 January 2013 and the 14th of February 2015. The first event will show forecast from the BTV 12 kilometer WRF model and also use the North American reanalysis grids. The second will rely mainly on the SPC mesoanalysis depiction of what occurred, which is an objective analysis based on the 1-hour RAP forecast and modified with current surface observations. There are two additional case studies available in our journal article if you'd like to see some additional examples of the snow squall events and their associated environments. So here is our first event from the 16th and 17th of January 2013. The 9-hour snow squall parameter forecast from the BTV 12 kilometer WRF is shown in the upper left, valid at 3Z on the 17th of January. With sea level pressure and surface to 2 kilometer AGL mean wind shown as well. The mosaic composite reflectivity is shown in the bottom panel, with a narrow convective band evident in the Canadian radar mosaic. The 9-hour BTB 12 kilometer WRF model forecast is consistent with the observed line of snow squalls. As a side note, the lake effect snow showers emanating off Georgian Bay are also highlighted by the snow squall parameter, as they are also a form of convective snow. For this case, though, we will focus mainly on the evolution of the snow squalls along the cold front further north across Ontario and western Quebec. Here is a base reflectivity loop from Landry, Quebec from 2340Z on 16 January through 0140Z on the 17th of January 2013. Corresponding nearby surface observations showing heavy snow with wind gusts up to 38 knots and visibility as low as 1/8 statute mile are shown on the right. Note pressure rising rapidly and the remarks coincident with these squalls. This 4 panel is from the NCAR valid at 3Z on the 17th of January. In the upper left panel we have the 0 to 2 kilometer AGL mean relative humidity as a color shaded field. We also have the sea level pressure, mean 0 to 2 kilometer AGL winds, and 925 equivalent potential temperature overlaid. In the upper right, we have the 0 to 2 kilometer AGL equivalent potential temperature difference color field, and shown with a colder shading for increasing potential instability. The sea level pressure is also shown. In the lower left, we have the 3 hourly surface isolobars or pressure change field. With that, we have the color-filled the surface convergence due only to the isolobaric component of the wind. This is the best way to see a mobile convergence signal not influenced by local terrain effects, because the reduction to sea level process necessarily removes these effects from the isolobaric field. The lower right shows the surface-based CAPE in joules per kilogram as the color-filled area, and 925 millibar positive frontogenesis in the blue contours. So clearly, the low-level air mass is very moist in the 0 to 2 kilometer AGL layer, along and ahead of a sharp cold front, per the image in the upper left. Steep low-level lapse rates can be inferred from the negative vertical theta E difference in the 0 to 2 kilometer AGL layer, shown in the upper right. This, by definition, means potential instability is present in the layer. In the lower left, we see a 10 millibar pressure rise behind the cold front across western Quebec, and an axis of 2 to 4 millibar falls per 3 hours ahead of the front. The presence of isolobaric convergence is due to the strong pressure rise fall couplet and is a function of the co-located frontogenetic circulation, with strong positive frontogenesis apparent at 925 millibars, as shown in the lower right panel. There is also a CAPE axis with 50 to 100 joules per kilogram values intersecting the frontogenesis maximum in the lower right, which tends to narrow and strengthen the low-level ascent within what is a thermally direct frontogenetic circulation. So in this case, we have all the ingredients necessary for snow squalls, and can see how the frontogenesis circulation is tied to the pressure rise fall couplet and the band of strong convergence just to the warm side of the surface cold front. We also see the moist convective aspect of this event, with surface-based CAPE and negative theta E differences with height in the lowest 2 kilometers AGL. So 4 panels such as this can be very useful in understanding how all the meteorological factors contribute to snow squall events. This image is also from the NCAR, valid at 3Z on the 17th of January. The snow squall parameter is the color fill on this graphic, and can be seen highlighting an area along the Arctic front and also in lake effect areas east of Georgian Bay in Ontario. The 3 hourly pressure change, again, shows pressure rises of 8 to 10 millibars across northwestern Quebec and pressure falls of 2 to 4 millibars downwind of the cold front. The isolobaric wind is a vector shown here pointing from pressure rises to falls, enhancing winds and resulting in convergence and ascent along the frontal boundary. The convergence will be strongest just downwind of where the gradient in isobars is greatest, which is typically very near the surface cold front position, as it is in this case. The upper left panel here shows a 12-hour forecast of the snow squall parameter, valid on the 17th at 12Z, from the BTV 12-kilometer WRF model, along with sea level pressure, 925 millibar theta E, and surface 2-kilometer mean AGL winds and knots. The corresponding observed radar reflectivity in the upper right shows good correspondence with the snow squall parameter forecast, and shows how the snow squall parameter forecast can be used as a tool to anticipate the occurrence of snow squalls. And just to reiterate the point that snow squalls are a mesoscale convective system, the photo at the bottom shows a gust front evident at the leading edge of the line of snow squalls as it crossed Lake Champlain around 13Z that day. This photo was taken from the Vermont side of Lake Champlain looking westward. The lake is visible at the left portion of the image. Meanwhile, low visibilities and falling snow are evident as a translucent region in the middle to right-hand portion of the image behind the leading gust front. The next case study we will look at is from Saturday, February 14th, 2015. This was a significant and long-lived event with snow squalls stretching from the southern Great Lakes all the way to the mid-Atlantic coast. The following slides highlight the snow squall parameter and other variables at a point after the full research to operations had occurred. So it will be an example of how to put these diagnostic tools to use using operational data sets. Since it was a Saturday, we would expect lighter traffic volumes in metro areas as compared to corresponding weekdays. This can directly affect the impacts and is something the forecaster should keep in mind beyond just the meteorology of the case. This is an isochrone analysis showing the approximate position of snow squalls each hour from 0800 through 2000 Eastern Standard Time on Saturday, February 14, 2015. The blue numbers show peak wind gusts, and the asterisk and caret symbols show locations of fatalities and injuries, respectively, in vehicle crashes directly related to the snow squalls. There were a total of 4 fatalities and 19 injuries spread across Indiana, Ohio, and western Pennsylvania in separate accidents and highway pileups. As you can see, wind gusts of 40 to 50 miles per hour were widespread across the region, while a few gusts in excess of 50 miles per hour were also observed. Here are some photos of the resulting devastation from that day as depicted in newspapers. Tragically, highway accidents resulted in at least 4 fatalities and 19 injuries. These are the types of situations we have the goal of ultimately mitigating as a result of better forecasting and forecast communication. This will require a sustained, multi-year, and multi-agency effort to help reduce these impacts, but is one that is consistent with the mission of the National Weather Service in its goal of creating a more weather-ready nation, with an emphasis on providing decision support services. Innovative ways of communicating the transportation hazard to motorists will also be needed, leveraging modern technology. We'll focus on these strategies and goals at the end of this presentation. Now, we did have a good idea of the potential for snow squalls on this day. Here is a look at the 12-kilometer NAM 63-hour forecast valid during the late afternoon hours on 14 February 2015. The models generally did a good job with the timing and location of the snow squall potential, as did the snow squall parameter, which is shown in the upper left panel in color shading. It is plotted with sea level pressure and isobars, and a strong surface pressure couplet can be seen, with 5 to 6 millibar rises across western Pennsylvania and Ohio, behind the front and axis of highest snow squall parameter values. A narrow axis of surface-based cape is also present, as shown in the lower left panel. Note that color table has been adjusted to highlight cape values of just 15 joules per kilogram or higher, as instability tends to be small in these events and in the wintertime, with cape usually not exceeding 100 to 200 joules per kilogram. There was frontogenesis present, though the color table in the upper right panel has some technical flaws. Model simulated reflectivity and QPF is shown in the lower right. So all in all, the model diagnostics pointed to a significant event, in this case 2 to 3 days in advance. From this, communication to state and local partners can potentially start early. The images on the following 6 slides all come from the RAP-based SPC mesoanalysis and shows what was available in real time as the event unfolded. This composite reflectivity loop covers 18 hours and shows several narrow bands of snow squall activity moving in cyclonic flow, initially from northwest to southeast and eventually from west to east. The snow squalls begin across lower Michigan and Indiana during the morning hours on the 14th. They then progress across Ohio, West Virginia, and Pennsylvania during the afternoon hours, eventually across the Washington, D.C. and Baltimore metro areas by early evening, and finally across southern New Jersey and the Delmarva Peninsula later in the evening before tracking offshore. With the shallow nature of these systems, with convective tops only 3 to 4 kilometers AGL, there is some beam overshoot making the bands look less spatially continuous at times. However, this is clearly a well-organized event given the long duration and linear nature of the squalls through nearly an 18-hour period. Consistent with all 36 events we had in the composite study, the mid to upper level jet axis in this case is south of the area affected by snow squall activity. The activity is also generally in the left exit region of the 500 millibar jet, which likely corresponds to upper divergence and associated ascent, likely contributing to the long-lived nature of the event. Winds at 500 millibars exceeded 120 knots in the jet core. In this loop, we see the low-level, surface to 3 kilometer AGL lapse rates, which steepen to 8 to 9 degrees Celsius per kilometer with daytime heating in advance of the boundary. This contributes to the low-level convective nature of the snow squall event. As noted earlier, forecasters should always look for the pressure rise-fall couplet. Strong pressure rises of 4 to 6 millibars per 2 hours are noted behind the frontal boundary, with a weaker but ever-present area of pressure falls ahead of the boundary, with values of 2 to 4 millibars per 2 hours. This is a very common scenario with strong and well-organized snow squalls. The pressure couplet is imbalanced with rises stronger than corresponding pressure falls. This aids in the forward propagation of the front and adds to the potential for strong gusty winds, as the isobaric wind will tend to add to the prevailing gradient flow. We also see deepening and consolidation of the surface low over the duration of the loop, which is generally a good indication of the favorable dynamics for frontogenesis and cyclogenesis. Here's the 925 millibar 2D frontogenesis with positive values shown by the purple contours. The frontogenesis shows increasing intensity as snow squalls became better organized across Ohio, West Virginia, and Pennsylvania during the afternoon hours. This is coincident with the left front quadrant of the upper jet and the steep lapse rates and surface-based instability present in the area. This is also directly related to the narrow, linear nature of the snow squalls, as observed on the composite reflectivity mosaic loop shown earlier. This further illustrates that frontogenesis is of first-order importance in these high-end linear snow squall events. Lastly, we have the snow squall parameter, which does a good job highlighting the area of greatest concern, especially as wind fields and instability increase during the daylight hours. You can see in these observations from Reagan National Airport that conditions deteriorated extremely rapidly just after 0Z on the 15th. Visibilities fell to 1/4 mile and northwesterly wind gusts increased to 45 knots. Likewise, temperatures dropped from the low 40s Fahrenheit at 23Z to 32 degrees Fahrenheit just after 0Z. This type of drop can lead to ice formation on untreated roads for many hours after a snow squall, as snow initially melts on warm pavement but freezes thereafter, especially if temperatures continue to fall with cold advection. So that is always something else to keep in mind as a forecaster in these types of events. The snow squall parameter is available in real time from several sources. For National Weather Service offices, within the AWIP's D2D volume browser in the winter menu, for any available deterministic models covering your forecast area. Online sources include the RAP-based SPC Mesoanalysis for current analyses, or the St. Louis University SIPS page for GFS and NAM forecasts at the URLs listed on the slide. WFO Burlington also offers the snow squall parameter within its suite of available output from the 4-kilometer WRF model. The domain covers the northeastern CONUS, from Pennsylvania north and east and adjacent areas of southeastern Ontario and southern Quebec in Canada. Before snow squalls develop across a forecast area, there are several operational strategies National Weather Service forecasters employ, often in tandem, to effectively get the message out about impending dangerous winter travel conditions. First of all, a special weather statement can be issued up to 12 hours in advance. Second, contact is made with state and local partners in law enforcement in the form of briefings or emails, which can heighten the awareness for those that need to make strategic decisions to mitigate the negative effect of the snow squalls on transportation. Social media and highlighting of the threat on National Weather Service web pages can also be effective in alerting the general public to snow squalls and their potential impacts on travel later in the day. The impact from snow squalls tends to be the most severe during higher traffic volumes, for example, at rush hours, and also when there is a rapid temperature drop with roadways initially near or above freezing, such that melting snow will form a thin layer of ice as temperatures drop, in what is sometimes referred to as a flash freeze situation. In this graphic, we have an example of a snow squall social media slide, which includes a brief headline, a description of impacts, a brief list of driving tips, and a map with isochrons showing the forecast arrival times of snow squalls, as might occur when co-located with an Arctic front. These are the types of efforts the National Weather Service will employ to keep the public aware of snow squall potential. I hope that you found this presentation on snow squalls instructive. Remember, there is a link to our journal article on snow squalls in the description box below. If you have any questions on this work, feel free to email us at the addresses listed here. So thank you for your time today, and best wishes in your winter weather forecasting and research endeavors.